Hi, my name is Jason Lusk, Product Marketing Specialist at TA Instruments. I would like to welcome you and thank you for joining us for today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access various content by clicking the Documents widget at the bottom right-hand corner of the screen. This includes a speaker bio and additional file downloads. If you need help at any time, click the question mark widget. Please ask any questions you may have at any time during this presentation by submitting them through the Q&A window. We will answer as many as possible at the end of the webinar. Our presenter today is Christopher Yakaki, Assistant Professor in the Department of Mechanical Engineering at the University of Colorado, Denver. Chris earned his PhD from the University of Colorado Boulder in 2007, focusing on the thermomechanics of shape memory polymers. He helped co-found MedShape Inc., a biomedical device company in Atlanta, Georgia, and served as the principal scientist for MedShape from 2008 through 2011. During this time, MedShape cleared several innovative shape memory polymer and alloy medical devices through the US FDA. In 2012, Chris joined the faculty at CU Denver. He has since been developing new methods of synthesizing liquid crystalline elastomers and characterizing their actuation and viscoelastic behavior. He also serves as an advisor and consultant for several biomedical device companies that focus on smart polymer devices. Chris has published over 33 peer-reviewed journal articles and has been awarded over $2 million in small business and academic research grants. The title for today's webinar is Characterization of Active Shape Memory Polymers. Chris?
Thank you, Jason, for that introduction, and thank you for joining us today. I'm going to be talking about the characterization of shape memory and shape-changing polymers. I was my PhD researched shape memory polymers for a long time, and now as a professor at CU Denver, I've been kind of moving into actuators such as liquid crystalline elastomers, and I'm going to talk about how we can use some of these instruments to characterize that kind of phenomenological effect of changing its shape. So, overview, we'll talk about stimuli-sensitive polymers, what is the shape memory effect, some basics of TMA, DMA, DMTA, how you could use that to maybe identify their structure, their thermal transitions, how you might characterize that shape memory effect, talk about some study results that we've published using these machines, and then just kind of wrap it up with some conclusions. So in general, stimuli-sensitive polymer is a material, or polymer material, that will respond to some stimulus, as the name might indicate. So that could be heat, it could be touch, it could be light, it could be changes in pH, it could be even electricity, it could be a lot of things. And so this is just an example of a plant. It's Mimosa pudica, I believe, and you can see when someone touches that plant that its leaves kind of contract and fold on in. Nature's really good at creating stimuli-sensitive materials, but we as humans can also create some synthetic materials and polymers that can do the same thing. So the most common, the most, I would say, well-known shape memory and active polymer would be heat shrink tubing. I think most everyone has used that. So you can see here in this video, some heat shrink tubing is used to kind of keep two wires together. And as it heats up, that tubing goes from a very large diameter to contracts down to a very small, kind of tight, form-fitting diameter. So that's probably your most common example of these materials. And where I tend to really like to look at materials and these applications is for biomedical devices. So if you look back, probably around 2002, Andreas Lendlin published a paper in Science, and they kind of proposed to use these shape memory materials as a suture. And so you can kind of see in this top picture that they took a poor rat here, they cut a laceration in it, and they sutured this wound together using the shape memory polymer wire. And the theory was, as they heated it up, using something like a hair dryer or a heat gun above body temperature, that suture would contract and pull the wound together. And the theory was that you could then design it so it pulls it together with the optimal force. If you use too little force, you get excessive scarring. If you use too much force, it doesn't heal properly. You also get excessive scarring. But in this case, you could kind of take it out of the hands of the doctor and put it into the design of the material to keep it as the optimal force to pull it together. Some things that I've looked at in the past was using these materials for soft tissue fixation. So here at the bottom left, you'll see it's a test tube with a cow tendon in it. And we insert a plug, and I just drew some black lines on that plug so you can see what's going on. But the black plug, or the shape memory polymer plug, starts out in an elongated, kind of skinny state. It was very easy for me to push into this tube. And as it heats up to body temperature, undergoes this shape memory effect. It's kind of getting shorter and fatter, and as it expands radially, it's creating a frictional fit to press the tendon into that tunnel. And in this case, it's applying a force to really kind of lock the tendon into place. Another example that we could use is for minimally invasive surgery, or stents. And in this case, there's a catheter here. I think it's a 22 French catheter. We packaged up a shape memory polymer, kind of rolled it up and inserted it into that catheter. We pushed it out, and again, we drew black lines so you can see what's going on. But as it heats to body temperature, you'll see that it kind of unfurls and it's expanding out. So it starts in its package shape. It was around 6 millimeters in diameter, and it's going to expand out to about 22 millimeters. So you can see for minimally invasive surgery, you could go in through a very small hole and then expand a device once you're into the place that you want to be. So those are just some applications, some potential applications that you could use this for that I tend to be interested in. So in talking about shape memory polymers, maybe a general definition would be that it's a polymer that can change its shape and or apply a force in response to that stimulus. And typically, most people like to use heat, but you could use lights, you could use solvents, you could use a lot of things. I tend to maybe refine that definition just a little bit and say instead of changing shape, I like to say it's recovering deformation, because really what it's doing is it's always returning to its original, you can think of its original equilibrium state or its original home base. And so as a result, it's not really a material property. I always like to say, I always wish I could come up with a material property and say it has a certain amount of, I don't know, yakakis to it or something, but it's not. It's really just an effect that's caused by the proper programming of the material that has the appropriate polymer structure. And we're going to discuss how we could maybe use these machines to evaluate, one, what is the structure, and two, how well that effect and that programming actually occurred. So just to maybe break it down, take a second and look at the shape memory cycle. What are you programming in? How do you actually achieve this phenomenon? Is basically 3 steps. We're going to start with just a regular polymer. I have it in blue. And what we're going to do is we're going to heat it up above some thermal transition, and I just kind of showed it in red to indicate that it was heated up. And we'll apply a force to this heated polymer and reshape it. So in this case, we're going to look at that kind of soft tissue plug where it kind of got longer and skinnier. So I apply a force and elongate this sample. And what we'll do is once it's into the desired shape that we like, we'll cool it down back to underneath its transition temperature and remove the force. And it should, if it's done appropriately and correctly, it should maintain that shape pretty well. And it can be stored indefinitely until you actually want to activate it, in which case you'll reheat above or near its transition temperature, and you'll see it'll go back to its original shape. And what you could do is you could do this over and over and over again. So they'll call it the shape memory cycle, because you could program it, store it, allow it to recover, and repeat that process over and over again. And usually when people think and talk about shape memory polymers, all they see is that last step of recovery. And so they think that's it. But really there's kind of some magic behind the scenes to get it to perform that shape change. So just to maybe kind of explain why you would go through those steps. So why might you want to heat before you shape the polymer? Well, what happens when you heat a polymer? Generally, most people know it gets softer. And so if you just looked at a glass transition curve of a polymer, and I'll talk a little bit more about this later, is at low temperatures or below its transition, you could say it's hard and it's glassy. And then as you heat it above a transition, in this case a glass transition, it gets softer or more rubbery. And so it gets a lot easier to shape in this case. And if you ask why does it get softer or more rubbery, you could look at what's happening to the chains themselves. So below the transition or cold, you have your chains with secondary bonds, you have a nice packing, you have less free volume. But as we go above that transition temperature, we break our secondary bonds and we kind of expand out our free volume. And in that case, it's a lot easier to shape. There's a lot more chain mobility. And so because the chain spacing gets a little bit further apart, because you lose your secondary bonding, because you have more free volume, it becomes softer and easier to shape. So it's just more of a practical nature that you can do it easier. And why might you want to cool for storage? Well, the classic example might be is what happens if we take a rubber band, we stretch that rubber band, and then we freeze it, right? So we get a really cold, definitely below subambient temperatures. Well, nothing should happen. It should stay in that stretched and elongated state. And why is that? It's pretty much the reverse of everything we just talked about. As we go below our transition, our chains will kind of collapse, we reestablish secondary bonding, and we kind of restrict chain mobility. So some people will say it's frozen into shape. That's kind of a more colloquial term, but I like to say it really restricts your chain mobility. And if you look at why does that last step, why does recovery occur? I like to use the example of entropy, right? So it's really a measure of disorder or chaos in a system. And so I like this fun example. You kind of have two offices, and you look at the office on the left, look at the office on the right, and you could ask, which one has higher entropy or chaos, right? And then you could also ask yourself, which one takes the least energy to either maintain or have? And so if your office looks like mine midway through the semester, it'd be this one on the right. That one's the easier office to maintain. And so I like to say materials, much like people, will kind of evolve to that state of the lowest energy. So kind of looking back at our polymers and our polymer chains, what happens when we stretch our polymer? When we stretch it, in this case, in the example I had compression, but in this case we'll stretch. And if we stretch a polymer, you can see we go from a very random chain alignment to very oriented left and right. So you can see in this second blue illustration that the chains are less random. They're more aligned horizontally. And so in this case, which state has higher entropy? Well, the original state does, and the stretched state has a lower entropy. And so when we go through recovery and we reheat the polymer, when we allow those chains to move again, when we increase the mobility, it will want to return to that lowest energy state. So first we got to increase the mobility by heating the polymer, and then the system says, hey, let's go return to that kind of high entropy, high chaos, high disorder, low energy state. And so some people will refer to that as entropy or rubber elasticity. So in looking at these polymers, these shape memory materials, some questions that you might want to answer is, what is the structure of the polymer? I said it has to have the appropriate structure. And usually you can determine that by looking at some of the thermal transitions that are present. You might want to look at, how efficient was your programming process of reshaping it, cooling it, storing it, and everything. And how much you measure or quantify the recovery behavior or the shape memory effect that everyone kind of sees and associates with these polymers. And so there's a couple techniques that I like to use in doing that. And sometimes these all get lumped together and people just call it DMA. But if you wanted to get a little bit more nitpicky, you could say, there's thermomechanical analysis where you have either a constant force or a constant strain, and generally temperature is your variable that you like to change. You have dynamic mechanical analysis where your force is now changing in a very kind of sinusoidal or cyclic fashion, and you're keeping a constant temperature. Or you have DMTA, dynamic mechanical thermal analysis, where we're both changing our force, that's being dynamic and sinusoidal, and our temperature at the same time. So some people generally will just refer to this all as DMA or dynamic mechanical analysis. I'll give you a couple examples of each one and how each one is useful for these systems. So some of the machines that I use is the DMA Q800. That thing's a workhorse. I really like it because I tell my students that the only way they're going to break it is if they just push it off the table. Don't try that though. And then the ElectroForce 3200. And so maybe first example, TMA, thermomechanical analysis. You can use this to determine the structure of our polymer and some of our thermal transitions present. So if you look at a very classic dilatometry experiment, you look at your specific volume versus your temperature. And glass transitions show up as a kink in the curve, and melting transitions tend to show up as a discontinuity or a jump in the curve. And so if you have just a zero force and you change the temperature, monitor your volume, this is what you would see for each of those transitions. So this is an idealized graph. So this is actually an experiment that we ran. So in this case, we just monitored the length of our sample, and we started at a very high temperature. I like to say in this experiment, cool, don't heat, because when you start at that high temperature, it'll relieve internal stresses. You won't get any weird, funky results in there. And cool very slowly. So in this case, we started at a high temperature, about 100 degrees Celsius, maybe a little higher, and cool at a rate of 1 degree Celsius per minute, or maybe even slower, with zero force. And so as we're cooling, you'll see there's a slope, or you can kind of look at it as your coefficient of thermal expansion or contraction as you're cooling. And what you'll see is a slight kink in the curve where our TG is. And the more slowly you cool, the kind of more distinguished that kink is. So that's why you want to cool nice and slowly. But this is it kind of gives a nice independent measure of TG that's not so sensitive on your heating or cooling rate, and definitely not sensitive on your frequency, which for DMA, which we'll talk about in a second, frequency can alter where your TG would be. But if you ran this as just kind of a slow TMA experiment, a lot of, I would say, constitutive modelers like to do this because it gives you a nice independent reference temperature of the glass transition. Moving on a little bit to DMA, dynamic mechanical analysis. So what we like to do is apply a sinusoidal force, a cyclic force, to our sample. And so here I just kind of showed, here's a little sample in 3-point bending. Usually though, I like to use the tensile mode, but 3-point bending works as well. I've done both. And so we're applying a sinusoidal stress. And so we have two maybe ideal situations. The first one is, what if you have something like a spring that is perfectly in phase or perfectly elastic, doesn't really depend on time, there's no kind of time lag or response. In this case, you would say your delta or your phase lag, we'll talk about that just in a second, is 0. Sometimes the example I give to people is you have two sine waves that are perfectly in sync, or for some reason I say it's two dolphins swimming side by side that are perfectly in sync together, going up and down. And so a spring would be a great example. You apply a force to a spring, it stretches instantaneously, comes back, and it responds to that force perfectly in phase. The other extreme example would be if you had something like a viscous fluid or a viscous damper. And so in this case, you're completely out of phase. So now your delta is 90 degrees. And so what you'll see here is that there's a big lag between when you're hitting your maximum force, that's when it's finally starting to respond. And so that would be your totally other different extremes. So you have a spring, you have a damper, and in mechanical systems, you always like to build things with those two materials. But in reality, somewhere we're going to end up in between, where it's not going to be perfectly in phase, it's not going to be perfectly out of phase, but a real polymer material will be somewhere in between, and that's what we want to measure. And so let's just go back to that first ideal case. If you had something that had a tan delta or a delta perfectly in sync of 0, as you apply a stress or you apply a strain, you can see those two responses, stress and strain, are perfectly linear up. So you can see I've drawn two arrows as if it was loading and unloading. And if you were to care about the modulus of that material, it'd be really easy to calculate. We would just use traditional definitions for modulus of a change in stress over change in strain, take that slope, and that would be our modulus. But if you have a material that is not perfect, it has a delta or is out of phase just a little bit, it's greater than 0, all of a sudden your stress strain curve looks like a circle or a loop, all right? And so that traditional definition of modulus doesn't necessarily apply. You can't just take a slope of a simple line. So in DMA, what we like to do is kind of define a couple new sets of terms of storage modulus, loss modulus, and tan delta. So all we're doing is taking a tangent of that phase lag delta. And so our storage modulus is just kind of our maximum stress divided by our maximum strain, and then we take the sine of that phase lag. Conversely, the loss modulus is pretty much the same equation, but we take the cosine of that, and your tan delta is the ratio of those two values. And so I like to maybe give a more simple term of tan delta being your damping or your dissipation. Some people just like to refer to it as the ratio of storage to loss modulus. Now, storage and loss modulus sometimes are funny to explain to people because storage modulus is something that's a real component, right? So people like to associate that with being a modulus. But loss modulus is often referred to as an imaginary component, which anytime you tell someone something's imaginary, you kind of lose them right away. So the classic example to kind of look at these two modulus values would be looking at a bouncing ball. So when you bounce a ball, you'll see that it comes off of a certain height, it had a stored potential energy, and then when it bounces, it returns to a height, but it's not as high as it started, right? And so the energy that was stored and recovered in the bounce, that really kind of relates to your storage modulus. And the energy that was lost in the bounce, that's what we look at as our loss modulus. And then that ratio between those two, that's our tan delta. So I have a video here. You'll see it on the right. And what we're going to do is we're going to drop two rubber balls, two elastomer balls from the same height here. And you'll see that one bounces really well. And it's continuing to bounce, going up and down. And the other one bounced about once, right? And so the difference between those two elastomer balls was that one had a tan delta that was very, very low, close to 0, the one on the right that continued to bounce, and one had a tan delta that was around about 1, all right? So it had a much higher value. And you can see that it dissipated out a lot of energy. Its loss modulus would have been a lot higher because it didn't bounce. It only bounced about one time. So that's just a nice, easy demonstration to kind of show you the difference between kind of what is storage modulus, loss modulus, and kind of what does tan delta actually mean. So in using DMA, I'll kind of highlight on one thing that I really like to use with the ElectroForce. In this experiment, we like to measure photo-crosslinking as it was happening for a polymer strip. And so here's the setup that we use. And one thing that you'll notice right away is that it has a very open test area, right? So the QA800, I love that machine, but it's harder to do a custom-made test setup. And so in this case, we have a very open design. And what we did was we exposed our polymer to some UV light. And you can really see that UV's reflecting off that sample pretty nicely. And what we did was we looked at those two waveforms, and we can capture those in real time. And so you can see our stress and strain waveforms down here on the bottom left. And we can measure, you can see there's a slight shift in the lag. We can measure that delta between those two waveforms. And by looking and using those equations that I just presented, we can investigate what's happening to its storage modulus and how it increases over time as we're photo-crosslinking this polymer. So here's a couple of the independent kind of cycles or the curves that I kind of showed as an example. And you can see at 0 minutes versus 1 minute of UV exposure to up to 10 minutes of UV exposure, you can definitely see the stiffness overall is shifting to a more higher slope, if you will. But what we'll do is we'll use that equation for storage modulus. We looked at it, and you could see that it increased from somewhere around 275 kilopascals, up to about 1.2 megapascals over 10 minutes. So it was really nice because we could measure how those photo crosslinks were being established in real time and how that was increasing the modulus very, very easily, you could say, in our polymer system. So moving on to just that third technique of, we'll have a sinusoidal force and changing our temperature at the same time. Usually we like to do this to look at a structure and the transitions in a polymer. So in this case, we have an amorphous network, so this is the one I tend to focus on quite a bit. And so again, we have our modulus, or I should say storage modulus, on our left axis and temperature on the bottom. And the two things that we'll like to monitor at the same time is the modulus and the tan delta or tangent delta. And so you'll see at the low temperatures below its glass transition, it's glassy. You can say, some people refer to that as glassy modulus. And as we go above the glass transition, it becomes more rubbery. As we talked about earlier, it gets softer. And one key kind of point to maybe highlight is that at the glass transition temperature, you'll see that the tan delta kind of maximizes. You'll see that nice little hump in the middle. Where that peak is where a lot of people like to define their TG, or glass transition temperature. So what's going on though is it's constantly analyzing those two waveforms as you're adjusting temperature. And I like that because it's a quick scan of your polymer. It usually takes anywhere between 45 minutes to maybe an hour and 15 minutes to get a nice glass transition curve and really identify what's going on in your material. One note that's a little different than TMA is this will be a little bit more sensitive to your heating rate and your frequency, right? So if you're testing at 1 hertz versus 10 hertz versus 100 hertz, this could shift a little bit. So that's why some people like TMA to just establish a reference glass transition temperature. For most of the stuff I test, I usually test at 1 hertz to establish my glass transition temperature. So I just showed you an amorphous network there, but when we talk about shape memory polymers, we're getting back to shape memory polymers, what we'll see is we have maybe 4 classifications of materials that we could identify with just a simple glass transition test running DMTA. Right? And so this is a nice little summary from a review published by Patrick Mather's group. And what they showed is the 4 different types of shape memory polymers that you could do. And so you'll notice from all of them that they have some thermal transition. So kind of at the top we have thermosets, and so in this case it's a crosslink network that just shows the TG. And then we have the second one is a semi-crystalline network that shows not only a TG but a melting transition as well. And on the bottom we have thermoplastics, where we have no crosslinking, no chemical crosslinking. You'll have some physical crosslinking of crystalline regions, but on the bottom we have thermoplastics, where we have a TG and a TM, and you can see then the storage modulus kind of approaches there. It really drops off as we heat it into that rubbery regime. And so in the first case we have just a thermoplastic, and in the second case we can have our block copolymer thermoplastic as well. So we have these 4 different types of materials that we could use as a shape memory polymer that we could identify very quickly just by running one glass transition test with these instruments. So if you're looking at what would be the appropriate polymer structure, so a couple things you might have noticed from those last curves is there should be a distinct transition, either it be glass or a melting transition. And in that there should be a drop in modulus of somewhere between, some people say 1 to 3 orders of magnitude. Typically I like to have it 2 to 3 orders of magnitude. And so I kind of have shown you a little picture here on the bottom right, and you can see something that's kind of a well-defined, very distinct transition, kind of labeled well-defined, and one that's kind of poorly defined. So you can see it's spread out over maybe over 100 degrees Celsius. It's not going to happen too rapidly versus one that's spread over maybe 30 to 50 degrees Celsius. There needs to be some cross-linking, whether it be physical entanglements in the polymer, whether it be a semi-crystalline domain, or whether it be a covalent bond. But you need that cross-linking to remember its shape so it doesn't just assume a new identity every time you heat it up. So in talking about some shape memory characterization, we kind of look at what's going on in these materials. So on the left axis here, I'm going to refer to stress and strain, and on the right axis we'll be referring to temperature. So I'll have 3 curves, but 2 of them will be kind of on the left axis, 1 on the right. And so generally what we'll want to do is, we'll heat the polymer up, and then we deform it. And so in this kind of step 1 region that you can see that the temperature is elevated. It's a higher temperature, easier to deform. And we apply either a strain or apply a stress, or they'll go hand in hand, and we'll assume a new shape. So in this case, let's say we stretch a material to a longer identity, and the stress goes up, the strain goes up. And once we get it at the shape that we want it to be, we'll start cooling the temperature down. So you can see in step 2, the temperature goes from an elevated state to a much lower state. And generally the strain should stay about the same. In this case, the polymer shrunk just a little bit as we were cooling it down. Our third step is we're going to unload the polymer. And so this will look like the smallest step I've labeled there in the middle. And what you'll notice is that the stress on that material is dropping to 0. And that'll be the storage state, as we talked about earlier with the shape memory cycle. And then finally, in that step 4, what you'll see is that the temperature is ramping up from a cold temperature up to a high temperature above, through its transition. And so what you'll see, the temperature is ramping up nice and linearly. And what you'll see is that the strain goes from a high strain, something that you've deformed the material, you've shaped it into what you wanted, and you can see that it's recovering its shape as the temperature is increasing. So it starts at a high strain and returns back down to 0 with heating. And so one way to kind of characterize this phenomena is to look at what we call the fixity, all right? And it's a kind of a measure or characterization of your programming step. And so when I say fixity, you want to kind of focus in on that step 3. I've kind of highlighted it here in yellow. And what you'll see is that when we unload the stress of the material, the strain drops down just a little bit. Now in this case, it doesn't drop down an extreme amount, but it definitely springs back some. And so that ratio of your unloaded strain to that maximum strain, or I could highlight it here with these 2 arrows, the ratio of those 2 strains can be referred to as your fixity. Generally, you would like a polymer to have a fixity value greater than 90%. You don't want to stretch this thing and have it recover back or spring back 50, 60, 70%. That wouldn't make a very good shape memory polymer. So, but generally, if you're above 90%, that's pretty good. Another thing that you could look at is the recovery stage, right? And again, this is what everyone kind of sees and associates and attributes to shape memory. So in this case, what you're going to be looking at is how much of that unloaded strain or that strain that you programmed into the polymer has recovered as a function of temperature. And so what you'll see here is that unloading strain I've drawn as that horizontal line. But then as it's heated up, as it's kind of changing its shape back to its original configuration, looking at that strain. So as it's recovering, how fast is it recovering? Is it recovering all the strain or not? Really, that's a measure of your performance in our recovery here. And lastly, what you could do as well is after you unload it and after you've stored the material, if you keep your strain, if you keep an external constraint onto your material and reheat, instead of allowing it to recover, right, that's one thing in shape memory is you can allow it to change its shape and recover. The other thing is you could use it to generate a force. So in this case, we're going to lock the strain in. So up in step 4, you'll notice the strain is not changing, but the stress that was once at 0 is now going to increase. And so you could also look at stress generation as we're increasing our temperature. Back one of I think my second example that I showed was the plug going into the tunnel with a tendon and exerting a force to lock it in place. This might be something you'd look at is how much force can we generate against that tendon to lock it in place. So let's talk about a couple examples of measuring some of these things. Sorry, not there quite yet. One thing I will notice or will comment on is, so we have three variables that we'll be looking at: strain, temperature, and stress. And it may have been, it's somewhat confusing. It makes you go cross-eyed the first time you see it. But one nice thing that you can do is you can run that complete shape memory cycle of changing your temperature, strains, and stress and monitoring either your recovery, whether it be a fixed recovery or free recovery, all in one experiment. And especially the Q800, this gets used quite a bit. So this is a paper I published back in 2009. We had a couple different networks that we infused with some magnetite, and we were potentially thinking about heating them using alternating magnetic fields. But you can see we have 3 different curves here, and each curve has some different level of magnetite in it. But what we did is created a 3D graph where you can see it started at a high temperature over where it says deformation in the curve. We apply stress, you can see the strain increases, and then as we cool the material back down, you can see where it kind of hits that back axis. That's where it's cooled and fixed, and you can see where we unloaded the material. It had a really good fixity, so during that unloading arrow, if you look at it, it doesn't drop too much. And then as we reheat it back up, you can see that recovery. So hopefully it doesn't make your eyes go too cross-eyed, but you can kind of graph all of these 3 variables in a 3D plot and run it as a single experiment in your machine, which is really quite nice to characterize the shape memory performance quickly. So now we'll start talking about some study results. Sorry, I got ahead of myself. So we talked about measuring photo-crosslinking a little bit earlier. So I'll talk about another study where we designed a couple networks with different cross-linking densities. And so you can see in our graph here, I have 4 networks, and I ran 4 glass transition tests, and they all have about equal glass transition temperatures, about 76 degrees Celsius. But the thing that should stand out is the rubbery modulus, or the storage modulus at a high temperature, changes. So it goes from about 9.3 megapascals all the way up to about 23 megapascals. And so our crosslinks, as I mentioned, help establish your permanent shape and help really provide your force to restore to that permanent shape as we reheat it during the recovery process. One way we can maybe measure how many crosslinks are there, the crosslink density, is by this pretty simple equation, just saying our density times our gas constant times our temperature divided by our rubbery modulus. So a rubbery modulus is something that's very easily read on these curves, and just by using that, we can figure out what is the, in this case, we're looking at the molecular weights between crosslinks, or looking at its crosslink density in these materials. So what we were able to correlate was that for these 4 different networks with 4 different rubbery moduluses, or 4 different crosslink densities, that when we measured the stress upon recovery, that increased pretty much proportionally with the rubbery modulus. So, so the original glass transition curves are here on the left. Over here on the right, you can see the different stress recovery. So I kind of took out everything with the programming and the fixity and just looked on what the stress generation was as we heated up these networks. And so in this case, again, you can kind of see that the lowest cross-linked, kind of lowest modulus network provided this lowest amount of recovery force, and that scaled pretty proportionally. So it had a pretty nice direct influence on these materials and on the shape memory performance, easy to see. Another maybe kind of study result that we showed is switching away from the amorphous networks, looking at some thermoplastic shape memory polymers. So a couple years back, I think it was about around 2010, a Formula Racing team wanted us to design a high-strength heat shrink tubing. And so here's kind of what they were looking for. I showed a picture here. So we have a thermoplastic polymer here. It's called polypara-phenylene. I got to give a shout out to Solvay Specialty Polymers for giving us this material. But it's a very strong, very high modulus, high TG polymer that's also a thermoplastic. And what we wanted to do with it is design it as a heat shrink tubing that had just superior properties to what you would buy commercially out there on the market, because they were trying to use heat shrink tubing to hold 2 things together, but didn't have the rigidity, didn't have the strength to survive the application that they wanted it in. And so what we looked at here is this polypara-phenylene. We run our glass transition test, and what you'll see looks like a very traditional test. Starts out glassy, becomes rubbery, somewhere around 230 degrees Celsius. That's when the material really started to kind of become a goo, and so the machine would stop, and if it could keep going, the modulus would have just dropped on down. And you can see its glass transition temperature is around 180, 185 degrees Celsius. But extremely high modulus at room temperature. This is probably one of the strongest polymers at room temperature. The modulus comes in about 5.5 gigapascal, so pretty high modulus and pretty high TG. And what we noticed is when we would program it and run our recovery test, in this case just free strain recovery, we didn't apply any forces to it, we just let it recover very naturally. It was very sensitive to our programming conditions. So I have 4 different programming conditions here. So it depends what temperature did we elongate or kind of stretch our polymer at. In this case, we could do 175 degrees and then just cool it very rapidly. So I say a 0-minute hold, or we have 175 degrees where we would program it and then kind of leave it at the high temperature for 100 minutes. And then also with that, we tried at 195 and 205 degrees. And what you'll notice is that some of those curves look pretty good. So if we deform our polymer, do all our programming and impart the new shape at 175 degrees Celsius, generally our behavior looked good. It recovered, I'd say, distinctly, quickly, and pretty much 100% recovery was achieved. But on the extreme, if we were to do our programming at 205 degrees Celsius and hold it there for too long a time, you can see it only recovered about 20-30%. And that was the most recovery we could probably get out of this system. So we wanted to look at how can we optimize and predict what the recovery would be in these systems. So one thing you could look at is your WLF coefficients. And so generally, when determining these coefficients, you will perform a series of tests over, I'll say, a reasonable time scale and reasonable amount of temperatures. And so when I say reasonable, what does that might mean? So generally, if you look at your frequency, most machines will go anywhere between about 0.01 hertz to 1 or 200 hertz. That's a reasonable range. Having a machine, having your Q800 or ElectroForce get to 10 million hertz, not going to happen. You need a specialized whole nother piece of equipment. But with WLF coefficients, what you can do is run a series of tests with at different temperatures in between that range between about, and I think this case we did between 0.1 and somewhere about 30 or 50 hertz at different temperatures. And so you can see these different curves. The ones at the very top would be at lower temperatures, and the ones at the very bottom would be at higher temperatures. And what you can do is you can shift these material responses according to these WLF coefficients using this nice little equation here. And that log AT is called a shift factor. So you can either shift it to the right or shift it to the left. And what you'll see is it forms what they would call a master curve, or a kind of a single reference curve. In this case, we chose 185 degrees Celsius to be that reference temperature. But what it should look like here is about a mirror image of your glass transition curve. But in this case, by just running a series of frequency sweeps over different temperatures, we can predict how the response would be with frequencies as high as 10 to the 7th hertz, which is ridiculously high. What we could also do, in this case, we used a DMA kind of format of looking at storage modulus and frequency and creating a master curve. We could kind of go back to TMA, and in this case, we looked at relaxation modulus. So we would stretch the polymer just a little bit, apply a small strain, watch the force or the stress relax, and calculate its modulus as that stress relaxes over time. And again, you can do this over a reasonable range of time. So generally, obviously like about 1 second to, I think in this case, it's about 10 to the third, so 10, 20 minutes, right? And so again, we at different temperatures, we would apply a strain, monitor the stress, calculate its modulus or relaxation modulus as a function of time in that 10, 20 minute range, and then shift to form a curve. Okay, so the nice thing about WLF coefficients is what works for your storage modulus will also work for your relaxation modulus, or really any viscoelastic function. So in this case, I kind of compared what our coefficients were for the storage modulus test and the relaxation modulus test. You can see those are very close and overlapping as well. In this case, we like to run this test a little bit nicer because you can really see where it dropped off. You can see at very high times, or you could say from the other thing, or high temperatures, that it is a thermoplastic polymer. You can see that modulus kind of goes to zero with a high time, or you could think high temperature as well. And so what we did after creating these master curves is we used the relaxation modulus master curve. I thought that one looked pretty nice. But you can use them to predict equivalent conditions. So I've kind of drawn 4 conditions on here, right here, but 3 are going to be equivalent. And so the easiest way to talk about TTS and this kind of equivalent time temperature superposition is to talk about, maybe use a silly example like baking, right? Now this isn't totally true, so if you're a foodie, don't yell at me, but some people would say, well, hey, if you bake something 350 degrees for 10 minutes, that might be the same thing as cooking pizza at 375 degrees for 8 minutes, right? So it would be equivalent conditions. Again, if you're a foodie, that doesn't always work. But generally, the concept should make sense to people that, in this case, a higher temperature would need less time, or a lower temperature would need more time. Same thing really works for polymers with time temperature superposition. So what we did here is we took the master curve for the relaxation modulus, and we have some starting points, okay? And the starting points would be, what would the modulus be? In this case, we just marked where the storage modulus would be on the relaxation curve. What would the storage modulus be at 175, 185, 195, or 205, right? So that's where our starting point is. And if you would take we'll look at the 175 example. If you take 175 and you hold it for 200 minutes, that would be the equivalent of starting at 185 degrees Celsius and holding it for only 8.5 minutes. Or looking at 195, starting at 195 degrees Celsius and holding it for 1.4 minutes. So those 3 sets of starting temperatures and holding times are all equivalent to each other. All right? And then I'll look at the results of that real quick. And so what you can see is for those 3 equivalent times, and temperatures, their recovery response was pretty much identical, right? So it initiated recovery at the same, its recovery rate was the same. They both recovered 90, 95% of the stored shape. And so what we could see is we could predict our programming and predict our performance based on this TTS, based on just running just a series of relaxation modulus, storage modulus tests, looking at our WLF coefficients. We could then predict how our performance was going to be, and we could know whether, if at a certain programming temperature, how much time we really had before we needed to cool it or whatnot. As that fourth example that's not plotted here on B, 205 degrees Celsius for 100 minutes. If you recall back from just, I think, 2 or 3 slides ago, had terrible recovery. And if you look at what's going on in the relaxation modulus curve, you can see that's well past where the modulus is relaxed to 0. You could look at it, it's totally rearranged, kind of looked at it as if it melted or kind of experienced flow. We can also apply a lot of these techniques to other polymer systems, and these are some materials that I've been focusing on in the last couple of years. This is liquid crystalline elastomers. And so with these liquid crystal polymers, we can still experience shape memory. So I kind of showed a little pathway here where we start with our material. In this case, it's not like the amorphous network. It actually has some kind of liquid crystalline white domains there. That's why it's white in the beginning. We can stretch it, we can release it, and you can see that we've imparted a new shape. And as we heat it up, it'll undergo the shape memory effect. So that's kind of what we've been talking about today. But there's also a pretty neat phenomenon that will occur, that if we keep a bias force or a bias stress, or in this case, just a simple weight onto our material, and we heat and cool, you'll see there's a reversible actuation behavior where with the weight, as we heat it up, it'll shrink or contract, and then as we cool down, it'll re-elongate. And so we can show a two-way actuator with these materials. And so I have a video here on the left, and what you'll see is that we have a material it's kind of been exposed. The binder clip will act as our weight in this demonstration or illustration. And so what you'll see is, as we heat it up, I'm just using a heat gun here. As it gets heated, the material will contract, and as we cool, the material will re-elongate. So using the machines, instead of going through a 3-step process, it's really only a 2-step process, or maybe even one, where we just apply a stress, change the temperature. So it's kind of more of a TMA type experiment. And so in this case, we perform these thermal sweeps under some constant force or stress and measure the actuation behavior. And what you'll see is, as we increase the stress on this material, our actuation behavior increases and increases and increases. So we can kind of look at the performance of our actuator when we apply some kind of biased force to it. And so what we wanted to do is we had a couple different networks, had different cross-linking densities. So the red top line had the lowest cross-linking, the blue bottom line had the highest cross-linking. And as we increased our bias stress for all these 4 different networks, you can see the strain actuation increased. Also, at the same time, as we increased our stress for these networks, or increased the cross-linking for these networks, the strain actuation decreased. And just by kind of multiplying your stress by your strain, it works out that you can also get your work capacity for these actuators. It's a very easy way to test and measure actuator performance. So you can see very, I'd say, kind of convincingly or clearly that as we increased our cross-linking content, our work capacity from kind of a volumetric standpoint decreased. So the networks with the lowest cross-linking content, experienced about 300 kilojoules per meter cubed versus much lower, about 100 for the high cross-link networks. So I'm just going to wrap it up here. Just want to look at DMA in general. It's really good for, most people know it, to characterize material properties such as modulus and glass transition, tan delta, things like that. Very, very simple material properties, maybe even structure in there as well. But it can also be used very nicely, and I hope I showed a couple nice examples, to characterize material phenomena. So one of them was the measuring photo-crosslinking as it happens, measuring the shape memory effect, or even actuation in different polymers. So I'd like to just acknowledge some of my funding that I've gotten through the NSF, NIH, State of Colorado, as well as some of my collaborators from University of Wyoming or Johns Hopkins. I think Ree is now at HIT in China. And my students, Mohan and Ravi. I'll give a quick shout out. Mohan's graduating, defending his PhD here in December. He's taken all the TA training courses. If you're looking for someone who's good with polymer science and testing and thermal mechanical characterization, he's your man. So yeah, if you're looking for someone, think about hiring Mohan. So now we'll switch over, take any questions from you guys on the webinar, and thank you for listening to me.
Thanks, Chris. A recorded version of this webinar will be archived and available online through the TA Instruments website. We will now begin the question and answer session of this presentation. Please submit your questions through the Q&A window. We will do our best to answer as many questions as possible. Okay, so we have about 10 or 15 minutes to answer a few questions that have come in. If you haven't asked your question yet, please feel free to do so. We should have time to answer them. The first question that we have is relates back to slide 17 from the presentation, and he asks, how do you get the curve on the right-hand side of the slide from DMA? And I think what he's referring to is the hysteresis curve.
Yeah, so thank you for that question. And just real quick before I follow up the questions, I think I made a slight error in one of my equations, and I tell my students always double check equations that I put on the board because usually I get them wrong when I write them out. So calculating storage and loss modulus, I think I might have switched my sine and cosine, so I apologize. But so yeah, the question was, I showed that hysteresis loop if you were to plot stress and strain. Oh, and here we go, it's pulling up for me here. And if you have no tan delta, it's just a nice linear line. You never have to worry about it. There's no hysteresis. But when you have a material that is somewhat visco or elastic or viscous, you'll get that loop. And so one kind of key difference between the two pieces of equipment to keep in mind is that the ElectroForce machine allows you to capture those individual waveforms and export that as its own little file. So I don't know if we can get that slide or advance the slide here to show how I captured it. But you'll see all the data points that I have captured on that waveform. That's one distinct difference between the Q800 and the ElectroForce is that the Q800 kind of, I mean, some people look at it as an advantage, nicely calculates all your properties for you, but you don't get those individual waveforms. The ElectroForce, we prefer in certain applications, such as the photo-crosslinking application that I showed, because we can monitor those waveforms and export them, look at them, and analyze them ourselves kind of after the fact. So that's how I got that curve for 17, and I don't know if, yeah, I don't see it popping up here right now, but that hysteresis curve that I got and looking at those two waveforms kind of side by side or overlapped at each other is a key advantage of using the ElectroForce machine.
Thanks, Chris. So the next question, excuse me, comes from Laura, and she asks, are there any shape memory materials where TTS does not apply?
Laura, yeah, that's a good question. So I would say that if you're dealing with materials that undergo a unique melting transition, that's where TTS is going to break down. So I could kind of give two examples of that. One would be for my liquid crystalline elastomer materials as they get heated up above what we'll call an isotropic transition temperature. It's really just a temperature where the liquid crystals melt. Okay, TTS will break down. So everything, all those functions will superimpose nicely until you hit that melting transition, and it kind of goes out the window. Same thing would happen with networks that have crystalline domains. Normally, I focus solely, I say normally, most of my research is focused on amorphous networks, so those amorphous materials shift with TTS very nicely. But when you have materials that have crystalline domains, as you go through those melting transitions, it can kind of go off the rails a little bit for you. So yeah, you kind of should be kind of careful on what type of material you're shifting TTS with.
Okay. So Nicholas asks a question here. It appears that most of your tests were done fairly quickly, short time between the programming and recovery stages. Can you speak to the amount of creep you would observe if you were to wait a longer period of time before recovery?
Nick, thanks for the question. I guess the creep, or maybe you would think of maybe a slow springback, would occur maybe, let's say, under two conditions. So it depends how you want to kind of look at the storage condition. If you're keeping an applied force on that material, there would be a chance that creep would occur. Right? So if for some reason during the storage condition you're holding a constant stress, you know, anytime you have a constant stress on a polymer, you face the risk that it could creep. Typically, and I'll kind of paint a broad stroke, typically you're going to be well below your glass transition temperature. And so the amount of creep that you would experience is, the time scale that you would need to have any noticeable creep would be extremely long. In terms of I'll say storage where you don't have a constant stress. We actually did have a paper on this, so yeah, I hate to say, oh, look it up in the literature, but we had a pretty interesting paper where we stored these materials about 30 degrees below their glass transition temperature for up to a year, and we monitored kind of what would happen over that course of the year. We didn't see any spring back in our materials. However, that doesn't mean the material's not slowly evolving over time. And so what we did notice is that for those materials that were stored for up to a year, there would be a slight amount of what they call physical aging. So the polymer itself would slowly kind of rearrange to I would say a lower energy state, but it actually had a noticeable difference on the recovery behavior. So your question is a good one to kind of think of how does that long-term time effects of influence the material. What we noticed is we didn't see a big influence on, was it slowly recovering over the course of the year. Those materials held their shape very well. That's a little bit of a consequence or maybe a result that our glass transition, had a distinct drop over about 3 orders of magnitude. And so by having a very kind of a short and distinct glass transition, by cooling about 30 degrees below that temperature, we wouldn't see any slow recovery over a very long time. But what you would see is the actual behavior, such as upon reheating, would slightly shift and slightly evolve. So yeah, that's a very good question.
Okay, the next question pertains to the WLF coefficients, and is how do you get those coefficients from the DMA measurements?
Okay. So,
and is how do you get those coefficients from the DMA measurements?
Okay. So there's 2 ways. TA does have a software that will do the shifting for you, which is nice. I guess it's kind of like I'll say the quick route of getting those. Then again, I also take those waveform files myself. I give them to my students and I say, hey, you're going to shift them yourself and trust but verify. So as I say, short answer without boring everyone. I believe it's the rheology package on the TA software that will do the shifting for you automatically. You can just run your TTS test, and like literally, it's just a couple clicks, and it'll do the best fit for you and shift it out. Maybe a long answer would be you could manually shift everything yourself and kind of plot all your shift factors as a function of I would say both temperature and look for intercepts. And it's a little bit harder for me to explain over the phone. Though I'd say there are a couple online. I hate to dodge the question. There are some online demos that will show you how to do it manually, and I'd be glad to kind of show you maybe an Excel file or send you an Excel file where you can kind of interactively kind of guess your shift factors, form your lines, look at your intercept, and get it. But long story short, they do have some nice software that'll just do it for you.
Okay, the next question that's come in is a little bit more general, but how do you run DMA on a brittle polymer?
Oh, excellent. So a couple things to keep in mind. So when you're saying brittle, so I'm assuming you're talking brittle from just like the macroscopic sense that if you try to stretch it too far, it'll break without undergoing much strain at all. So two things that I tend to maybe worry about is, one, when you clamp that material, make sure you're not over clamping the material, right? And so a lot of times, even elastomers, and you might say, hey, elastomers aren't brittle, but when you heat a polymer up to a high temperature, let's say above its glass transition, and it's very rubbery, as you start applying a stress to that material, you'll notice that it'll kind of break pretty quickly. It won't undergo much strain, and you'll be like, well, it seemed very rubbery, but it was brittle. So that's one kind of thing you might worry about. Or maybe the polymer is just very glassy and like just a traditional sense that it breaks easily. So one thing that maybe some people run into with polymers, I said, like maybe quote-unquote brittle, break fairly easy, is make sure it's not being clamped too hard. Like, there's a couple tests that we can do to avoid that, especially if you're running it in tension, is we'll make sure, like almost always, we wrap the ends with just a little bit of tinfoil, or we'll switch the grips around backwards so the serrated edge isn't digging into that material. That's just one maybe just practical aspect to try to make sure that the testing itself isn't breaking it. The other thing is make sure that we're not applying a very high dynamic strain. And so just because a material is brittle doesn't mean it can't undergo some strain. It just means it can't undergo any plastic deformation. So what I would then suggest is put your strain amplitude or your dynamic amplitude down. Now, I think the max, that if you read in a book about DMA by, I think Kevin Menard wrote a nice book on it, he says never go above 0.2% dynamic strain. So if your material is quite brittle and can't undergo a high amount of strain, I would just then kind of recommend to get it lower, 0.1 or even 0.5. I think that the trick would be to get a good measurement that as long as your amplitude overall is at least about 2 microns, you'll be okay. You'll get a good measurement. So, yeah, I would just make sure the gripping interface isn't causing any damage, and you're not, I'd say, damaging or cutting into the sample while testing. And then 2, lowering your dynamic strain so such that you're not causing large deformation onto that material.
Okay, great. So that appears to be it for the questions that have come in for today. I would just like to once again thank Chris for his time today. I would also like to take this opportunity to thank each one of you for attending. We certainly very much appreciate the time that you've taken to join us. If there were any questions that we weren't able to get to, that you weren't able to submit at this time, please feel free to send them to us at electroforce@tainstruments.com. Chris has agreed to answer some of those questions that come in after the fact, so we'd be happy to do that. We have one more question. We hope that you've enjoyed today's webinar and look forward to having you join us again in the future. Thanks very much.